In this video, we are going to focus on the functional group that is called alkanes. We are going to explore their physical properties, and additionally, we're going to start learning how to name them. The properties of alkanes include that alkanes are nonpolar molecules. Alkanes, as we saw previously, are formed by having carbon-carbon and carbon-hydrogen single bonds. Since a carbon-carbon or a carbon-hydrogen single bond is a nonpolar covalent bond, all alkanes are nonpolar. When we look at their interaction with water, since water is a polar molecule, all alkanes are insoluble in water. It is honestly also known that they're less dense than water because their densities are less than 1. They are flammable in air, and we're going to see later in the chapter what that means in terms of reactants and products. And alkanes are present in crude oil. The image that we see on the right side of the slide is just representing a crude oil spill in the ocean. Since we know that because crude oil contains alkanes and they're less dense than water, these different yellow patches that you see in the image represent the alkanes that are present in crude oil, which they will be floating on top of that ocean water. Let's now proceed to look at alkanes from the point of view of how to name these important organic compounds. Alkanes, as I just expressed, are hydrocarbons that have carbon-carbon single bonds and carbon-hydrogen single bonds. They have a general formula, which is known as CnH2n plus 2. What that value of n represents is any whole number from 1 all the way to infinity. So alkanes have a continuous chain of carbon atoms. And they are also called saturated hydrocarbons because alkanes have the maximum number of hydrogen atoms that a carbon atom can hold. In table 11.2, it is actually representing the systematic name, or what is called the IUPAC name, based on the agency that determines the names for organic compounds for the first 10 alkanes. It is essential when we're learning organic chemistry that out of this table, you understand what are the prefixes that are assigned for the number of atoms. And eventually, as we build our nomenclature rules for the different functional groups, we're going to learn how to name compounds. When it comes to this table, I will suggest that you memorize, as I mentioned, the number of carbons, the corresponding prefix, and in a moment, what is the ending for naming a particular functional group. So when we're naming alkanes, the ending of the name is going to be ane. So we can observe as we look through the table how each one of these names end in A and E because that is the suffix that is added for any molecule that is an alkane. The simplest alkane only has 1 carbon atom because essentially this is where N equals 1. So if the molecule only has 1 carbon atom, according to the equation CnH2n plus 2, then that carbon atom is going to have 4 hydrogens. When your molecule has a single atom with 4 hydrogens, for 1 carbon atom, the prefix is meth. And since it is an alkane, the name of this molecule is methane. An alkane of 2 carbon atoms. The prefix for 2 carbon atom is F. So if you have a continuous chain of 2 carbon atoms and it is an alkane, that is called ethane. 3 carbon atoms, the prefix is prop. So the alkane of continuous chain of 3 carbons is called propane. 4 carbon atoms, the prefix is bute. And when you have 4 carbons in a row for an alkane, the name is butane. For 5, 6, 7, 8, 9, 10 carbon atoms, specifically, those prefixes are going to be Greek. Pent for 5, hex for 6, hept for 7, oct for 8, non for 9, dec for 10. And we can see that their corresponding alkane names for straight chain carbon atoms of those values. For 5 is pentane, 6 carbon atoms in the row is hexane, 7 carbons in a row is heptane, 8 carbons in a row is octane, 9 carbons in a row is nonane, and lastly, 10 carbons in a row is decane. You can see here specifically the condensed structures for the alkanes from 1 carbon all the way through 10. Alkanes, in addition of being just continuous chains of carbon, carbon, and carbon hydrogen single bonds, they can also have side groups, which are called substituents or branches. The most common term that we utilize is called substituent. Let's now focus on the 2 structures that we have on the right side of the slide. First, you have the model for the first molecule and also the second one. Then we have the condensed structure for both of these molecules. If we look at the chemical formulas for both of these molecules, this is C4H10. Where do I get that? As you can see, 1, 2, 3, 4 carbons. 3 plus 2, that's 5. Plus 2, that's 7. Plus 3, that's 10. If we look at the molecule on the bottom, it's also C4H10. 1, 2, 3, 4 carbon atoms. 3, 6, 9, plus this one. This hydrogen, that is 10. Now, looking at the molecules, we can see that the connectivity of the atoms is different. Thus, the 2 molecules are going to have different names. From the previous slide, if we have a molecule that has 1, 2, 3, 4 carbon atoms, what is the alkane name for it? If you determine butane, you're correct. Now, the bottom molecule is not called butane because what we see here is that the longest continuous chain of carbon atoms is not 4. It's actually 3. And it doesn't matter if I look at it from the point of view of this direction, meaning 1, 2, 3, or I look from the point of view of this direction, it's still 1, 2, 3. For simplicity, I'm going to highlight this as the longest continuous chain of atoms that we have in this molecule. Now, if we have 3 carbons in a row in a continuous chain, that specifically is called propane. Now, if I highlight that propane chain, I see that there's something sticking out of it. That is what is called a substituent. A substituent of one carbon atom is called meth for a single carbon, YL because it is a substituent. So a CH3 sticking out of the longest continuous chain of carbon atoms, that is called a methyl group. Now, this methyl group is not specifically in at an end, it is actually right in that middle carbon. So when we are trying to name this alkane, what we need to do next is going to be number my longest carbon chain, the one that I highlighted in yellow, specifically from the end that it is closest to the substituent. In this particular molecule, it doesn't matter if I go 1, 2, 3 or 1, 2, 3. This CH3, in other words, the methyl group is still on carbon 2. So as a prefix of that propane longest continuous chain, I have to say, well, on position 2 of that propane, I have a methyl group. And that's how we name alkanes with one substituent. I'm going to formally introduce what are the rules for naming alkanes with one substituent, but I wanted to give you a preview. Methyl groups are not the only functional group, not the only substituents that you guys are responsible for. In this course, you need to know all the substituents that are present in table 11.5. As I just illustrated in the previous example, when my substituent is a CH3 connected to a parent chain, that is known as a methyl group. If my substituent or branch out of the longest carbon chain is a CH2, CH3, remember that this corner was connected to the parent chain, that is known as an ethyl group because it has 2 carbons. Next one, if I have a CH2, CH2, CH3 connected to a parent chain, or meaning the longest continuous chain of carbon atoms, that is known as a propyl group. Prop for 3 carbons, YL for substituent. Now, instead of connecting to the end carbon in a propyl group, if I'm connected through the middle one, that is known as an isopropyl group. Understand that halogens can also be substituents for alkanes. So if you have a fluorine substituent, that is called a fluoro group. Chlorine is known as a chloro group. Bromine is known as a bromo group. Lastly, iodine is known as an iodo group. Let's now formally introduce what are the rules when I'm naming alkanes with one substituent. Step number 1. When you're given an alkane and there's only one substituent, you must find the longest continuous chain of carbon atoms present in your molecule. Next, you have to number the carbon atoms starting from the end that is nearest a substituent. To name the molecule, you need to give the location and the name of the substituent as a prefix of the main chain, meaning the longest carbon chain, and the location number and the words need to be separated by a hyphen. Let's actually explore the 2 examples that we have in the following slide. Here I have a condensed structure for an alkane. As I explore this molecule, I can detect that the longest carbon chain can extend from this side of the molecule or from this side of the molecule. Regardless of which one you select, you still have as your longest continuous chain of carbon atoms 1, 2, 3, 4, 5, 6, 7, 8 carbons. Let me illustrate the other one. We have 1, 2, 3, 4, 5, 6, 7, 8. It is essential that you practice how to name organic molecules and you learn to detect what is the parent chain. For simplicity, and because either parent chain is correct, I'm going to select the one that is extending from left to right, but understand that the other one, if selected as your parent chain, you will have the same name for the structure. The first thing that I like to do is highlight that parent chain. The rules tell me that I have to number the chain starting from the end that it is closest to the substituents. So in this molecule, I have to go 1. Let me erase that, retry it. There you go. 1, 2, 3, 4, 5, 6, 7, 8. And I have to go right to left in the numbering because my substituent is closer to the right side of the molecule. Now, since I highlighted the longest parent chain and I know that there's 8 carbons, then that means specifically that my name is going to end with the word octane for the 8 carbons in the parent. As a prefix of that, I have to give the location and the name of the substituent. Outside of that highlighted area, I have a connection that looks like a CH2 connected to a CH3. That is called an ethyl group. And since my ethyl group is on position 3, the name of this compound is 3-ethyl octane. Understand that even though here it looks separated just because of how I build the word, this is actually one sentence. All these words come together. Take a moment and name the following compound. In this molecule, my longest parent chain is 1, 2, 3, 4, 5, 6. That means that when I name that parent chain, that main chain, that is a hexane. My substituent here is a chlorine, which that is called a chloro group. And its position is at position 2 in that main chain. So the name of this compound is going to be 2-chlorohexane. Make sure that you practice with the worksheets. I want to do at least one more of the examples that you see here. We have the following structure. Take a moment and identify what is the longest continuous chain of carbon atoms present. At first, you may identify that you have 1, 2, 3, 4, 5, 6, 7 carbon atoms. But that is not the longest continuous chain of carbon atoms in this molecule. Because you can also do 1, 2, 3, 4, 5, 6, 7, 8. That is the longest carbon chain in this molecule. Now I'm going to number it, starting from the end that is closest to a substituent. That means that my parent chain in this occasion, let me just highlight it, is an octane. At carbon number 4, I have a CH2 and a CH3. If you're not able to visualize that after I finish naming it, I'm going to put in the carbons and hydrogens to ease the visualization, but understand that you need to be able to go from skeletal to condensed and vice versa in these type of questions. So at carbon number 4, as I mentioned, you have a CH2 followed by a CH3. That is called an ethyl group. So the correct name for this molecule is 4-ethyl octane. For those of you that benefit from looking at the carbons and hydrogens, now I'm going to place them in the molecule. Make sure that you practice naming alkanes with one substituent. Another important skill is, if you're given the name, know how to draw the condensed and skeletal structure for your molecule. I'm going to use as an example the very first systematic name, in other words, the IUPAC name that we have as an example. Here we have 1-chloropropane as the structure that I need to draw. So if my structure is 1-chloropropane and I need to draw specifically the condensed and the skeletal structure for this molecule, the first thing that I'm going to draw is the main chain, meaning the longest continuous chain. In order to address that, I'm going to look at the last word, propane. Propane suggests that there are 1, 2, 3 carbons. Remember that in the condensed structure, you're going to illustrate all of the atoms, the carbons and the hydrogens attached to the carbon, and also the halogens, like in this one. So I drew my propane, then I proceed to draw my chlorine. So on carbon number 1, I put a chlorine. Now understand that you could have drawn the chlorine pointing this direction. You could have point the chlorine in this direction. So it's basically your artistic expression, whatever direction you are going to place that chlorine, as long as you put it on the first carbon in the molecule. Since in the condensed structure, I'm going to illustrate all the atoms, then I need to fill the octets for the carbon atoms. Since this first carbon atom only has 2 single bonds, it receives 2 hydrogens. The next carbon atom, since it has 2 bonds, also receives 2 hydrogens. The last carbon atom, since it only is bonded to 1 single bond, it will receive 3 hydrogen atoms. And that is the condensed structure for 1-chloropropane. Let's now draw the skeletal structure. When it comes to the skeletal structure, the minute that your writing utensil is on the surface of what you're writing with, that is going to be carbon number 1. Next, you're going to draw a line to the second carbon pointing up. Next, you're going to draw down the next carbon atom. So those are the 3 carbon atoms in my propane. And it is okay to draw those dots as guides. Next, I'm going to write next to carbon number 1, the chlorine. For me, I'm just going to draw it like this, but it is, again, your artistic expression. If you want to slant it to the side, pointing down, pointing up, as long as you put the chlorine on the first carbon, you are writing the correct structure. As you can observe, that is the structure for 1-chloropropane.